Hey everybody, and welcome back to Linear Algebra Online. So today we're going to talk about basis a little more for abstract vector spaces, as well as the dimension of an abstract vector space. And what you're going to see is a lot of this stuff is just going to extend really nicely from everything we've basically learned this year so far. So let's get into it. So a lot of times in the practice of linear algebra out there, you have like a certain abstract vector space you're working in, and you need to find a basis because everything in your abstract vector space needs to have like those building blocks to work off of, and so we need to be able to solve problems like this one, where I basically here I'm giving you a set S, and A and B in here are just real numbers, let's say. And so this is some abstract vector space, some polynomial abstract vector space. And what we need is we want a basis for this space, okay? And here it's really not too bad. Basically what you can do is you can group like terms, okay? So notice that I can pull an A out of, do 1 plus x cubed there. And then I can add to that b, take a b out of x minus x squared, all right? And, that's just kind of right from here. And then, honestly, this would sort of describe it. So anything in here is like a linear combination of 1 plus x cubed and x minus x squared. And so your basis can literally be that set. It's basically a set of 1 plus x cubed and x minus x squared. You could check that they are linearly independent if you want, but it's pretty clear that they are. This one has cubics and this one doesn't. You're not going to be able to get cubics here. And likewise, this one doesn't have quadratics, but this one does, so you're not going to be able to get quadratics. So, it is pretty clear that they are going to be linearly independent from each other. And what we're going to start seeing soon is that this is going to connect back to Rn. So this is the answer to the problem right here. But what we're going to kind of see is that we can connect back to Rn and think of this as the basis 1, 0, 0, 1, and then 0, 1, negative 1, 0. So the 1, again, is this one, 0, no x in there, 0, no x squared, 1, x cubed, same thing here. The way you want to think of this is it's sort of a plane living in four-dimensional space, right? The same way this is a plane living in four-dimensional space. So I just want to make that connection because I think we're more used to thinking about these vectors rather than these vectors. But all the stuff where you've kind of learned about take orthogonality or something, like W perp is going to have to be a two-dimensional space because of this subspace right here, because we need to account for 4 dimensions total. The same way that W perp down here is going to have to be two-dimensional to account for the 4 dimensions that we have in this space. But anyways, this is a basis for that set S. So one of the things that we're actually kind of building towards is something called change of basis, and there is something really nice, and I've mentioned this term in isomorphism, and I will define it eventually, but it takes some time to get there. But what an isomorphism generally is basically a formal math way to kind of go between vector spaces, and in different vector spaces, you have different bases. Bases, I guess, is really the plural. Just like here, and this is a basis for this just like this is a basis really for it. Like it ends up being that these two things functionally are the same, structurally are the same, I think is a better word there. And there's something called change of basis where we go back and forth between them. And we need to know how to make these coordinate vectors with respect to a new basis, okay? And basically all this is like if you have a basis B, or, this set of vectors V, and you have some vector V in capital V, the vector space, then that vector should be able to be written as a linear combination of those basis vectors, right? And the C's that make up your linear combination are what we call those coordinates of V with respect to B. And so we can put those in here. We've seen this before. This isn't anything particularly new, but if you have like I hat and J hat, right? Let's take the vector, 1, 2, let's say that's 1, 2, right? 1, 2 is built out of one I hat, right? This thing is built out of one I hat plus two j hats, right? And so we get V with respect to that standard basis there, right, is equal to 1, 2. That's just how we're used to writing. That's how we think of 1, 2. And it's just built out of one of these basis vectors plus one of these. In polynomial space, okay, if we want to write P of x with respect to B, where P of x is 2 minus 3x plus 5x squared, and with this, the B is the standard basis for P2, that's very similar to this kind of thing. We would basically just say, well, it takes two, x's, right, minus 3, nope, sorry, that sounded wrong. Two ones, there we go, minus 3 x's plus 5x squareds, okay? And remember that, the standard basis for this is just like 1x squared. And so this V with respect to the standard basis B, for that is you just peel off these numbers. So it's 2, -3, 5. Oops, let's do that. That is the C's. Those are the C's that you kind of have as the built into that linear combination here to get 2 minus 3x plus 5x squared. You could do the same thing for P sub n, like nth order polynomials, right? You would just basically have a vector that looks like a sub 0, a sub 1, all the way down, right, to a sub n. You would just basically be able to pull out these coefficients and pop them in here, whatever those numbers are. Just think about it back with numbers, and all we're doing is we're sort of abstracting what those basis vectors look like. And we still get something that kind of looks like numbers that we're used to, but it's a little bit different. And this comment up here about this computer thing, I don't know if you read that, but the benefit of linear algebra is really that we can take things like this polynomial space, and we can do function spaces of all sorts of different functions, really, not just polynomials. But we can abstract them and start getting basically tables with numbers in them, which computers handle really well. And so the idea is like in practice, in the real world, you take abstract vector spaces, you figure out some way to represent them with a table with numbers, then you let a computer do something, you get some result from the computer, and then you might go back and interpret it back in the polynomial space that you have. And there's vector spaces out there with sines and cosines and all sorts of other different weird things. But all of those have these nice isomorphisms that we can build up, which then let us get this kind of stuff and then we can let computers do stuff and then go back to the interpretation step where the human beings have to basically take over and be like, okay, well, what does that mean about my polynomials or my sines and cosines or whatever the thing is? It's a really, really powerful result that, honestly, when they figured it out, it completely changed so much stuff. And nowadays, actually even more so, because computers are getting so insanely fast that this kind of trick becomes increasingly more prevalent. So as a more interesting problem, I want to do a similar thing, but now, so this is my polynomial, okay, but I want to write it with respect to this basis, so not the standard one, because with the standard one, right, it would just be 1, 2, negative 1. The idea here, right, is you have like C1 times this 1 plus x, then you have plus C2 times x plus x squared plus C3 times 1 plus x squared. And we basically want to know what are the c's that get me to 1 plus 2x minus x squared. Okay? And we've seen this kind of thing before. Basically what we got to do is we got to group like terms. Okay, so if you look at the constants, right, you would get some out of here and here. Okay, so you would get like C1 plus C3 needs to equal, so this, and this needs to equal this, 1. Let's do x's. So here's an x, here's an x. C1 plus C2 needs to equal 2x, right? And last but not least, x squareds. What do we got? C2 plus C3 equals minus 1. Actually, I just shouldn't write that x. So I'm just equating the coefficients of the variables, right? I need, one of these C2s plus one of these C3s to equal negative 1 over here. And then we get a matrix, right? We can build a matrix of 1, 0, 1. We're going to augment this, right, with 1 there. And then 1, 1, 0, augmented with 2. 0, 1, 1, augmented with negative 1. And then we just do like standard RREF stuff, okay? And if you RREF it, you'll see that basically C1 has to be 2, C2 has to be 0, C3 has to be negative 1. And so now you can get your coordinate vector with respect to the basis C. So we would write it this way. We would say that polynomial P of x, script P, C's are hard, with respect to C would equal 2, 0, negative 1. And you could check it. You could put a 2 in here, a 0 here, and a negative 1 here. So really, it's not that hard to check. You can just do this stuff plus this, and you'll see that you get it. But yeah, this polynomial with respect to that basis is 2, 0, negative 1. Okay? And then again, like you let a computer take over and do some sort of stuff from there. But that's basically what you need to do in order to write vector spaces with respect to other bases. Okay? So another thing I said I wanted to talk about here was dimension, and it's very much the same thing that we've seen. Dimension is still just the number of vectors in a basis, okay? And so just to kind of make up a few examples to kind of get you used to it here. So if I was to write down some examples of vector spaces that are more interesting, so other than Rn, that have dimensions 1, 2, 3, 4, and 14, there are literally infinitely many choices. I'm just going to make some up on the spot here. So let's do, dimension 1. Let's do polynomial space 0. So this is literally just, the basis for this would be like a 1. it's basically just your, your constant polynomials. And that space, has dimension 1. For 2, let's do, we'll do one more polynomial one just to make the connection more clear. So if I do P1, right, that's like the constant polynomial, so you could take 1 and x there, right? I think after this I'm going to stay away from polynomial ones because it's kind of boring, but that would have dimension 2. For 3, you could do Z3, which we talked about briefly. That is like the integers 0, 1, and 2. But here you would have to specify that this is over Z3. We had a problem where we talked about how Z3 over Z or something is not a vector space because of like closure with scalar multiplication. But if you do Z3 over Z3, then it's actually a vector space. So that's fine. And these ones I'm basically, up here I'm sort of assuming that they're real valued polynomials. So those ones would be over R. If I don't specify what it's over, I typically am implying it's over R. That's kind of how I think about this unit. For 4, let's do M2 by 2. So M2 by 2 is like your set of 2 by 2 matrices, and here you're thinking of them as real valued matrices. But a basis in this one is just you need basically a 1 in each spot, which would then give me 4 matrices, right? And then last but not least, that one. And so this set is a basis for M2 by 2. And then for 14, let's do, so you can do M, like M by N for any one you really want, and it's always a vector space. You can do then a 2 by 7, okay? So you want to think of this as, just like basis vectors here are basically like 0, 0, 0, 1, okay? And then I would need, 3 more zeros, and then 0, 0, 0, 0, 0, 0, 0. So I think I did that 1, 2, 3, 4, 5, 6, 7, yes. So basically you would tack a 1 in these different spots, right? And you would have to have 14 matrices like that. This would be a 14-dimensional vector space. And actually, in general, whenever you do any of these M by N ones, the dimension of that, right, is going to just be Mn, right? And that's actually true, and you could prove it and stuff. But and again, here I'm thinking real valued matrices. So tons of different examples out there, and they get only weirder as you go in math. You'll learn other ones if you keep taking courses like this. But all of these, I honestly just, when I look at this, I think of R1. I think of the numbered line. When I look at this, I think of 2-dimensional space. When I look at this, I think of 3-dimensional space. This is 4-dimensional, this is 14-dimensional. It's just weirder representations of what a vector can be, but you want to always kind of go back to what you know well, which is Rn. And that is that thing. We're going to tie it in eventually, I promise, with an isomorphism, and I'll formalize this connection and how you can actually formally assume that there is this connection between these things and this one and R1 and stuff like that. All right. These are just properties basically, of vector spaces with dimension n. And they're all very intuitive, and the book proves some of them, but you can read them there, but they're not, honestly, super enlightening. I'm not going to worry about it right now. So I suggest you pause and like read these and make sure they make sense, but they're not anything that is totally new to us. I don't know, I'll just take this one. Any linearly independent set of exactly n vectors in V is a basis for V. Yeah, because if it's an independent set of vectors and you have exactly n and the dimension of the vector space is n, then basically, think R3 or something, right? You have 3 vectors that are linearly independent, right? And they're going to be a basis then for R3. So all of these are pretty intuitive. I don't think I really need to go into how they all work. This kind of thing is also pretty common. A lot of times in practice, you'll be working in some vector space and you'll need to extend it to a basis. So you kind of get to the point where you know what a lot of these dimensions need to be. And one way you can do these problems is you can just tack in what the standard basis is for like a space. So here you could tack in 1x and x squared. So then we have 1 plus x, 1 minus x, 1x, and x squared. And then what you can do is you can basically you can go through like the construction that we've sort of done before, where you basically turn this into a basis by you can like set up a matrix RREF things to get to figure out if the set is linearly independent or dependent, and then you can see you can set up a span argument, right? And the idea is like you want to take like a of 1 plus x plus b of 1 minus x plus c of 1, right? Plus blah 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 blah, and you want it to equal like a plus bx plus, or not a, I have to use something else now. C1 plus C2x plus C3x squared. And then you can like solve for a, b, and c like over here. But we can also you get to the point where you kind of get more intuitive and better at these things, and I can see that like this set, right, is missing quadratics, and I need quadratics to get, I'm not going to be able to add these together in any way to get a quadratic. So here, you can also just extend it this way. You can just be like, okay, well, 1 plus x and 1 minus x are linearly independent, for sure, right? And so if I just tack in an x squared, then I should have a basis for P2, right? And so there's ways to do it where you just throw all of the standard basis in and then like take out what you don't need. But you can also just sometimes get intuitively good at like knowing what do I add in to make it a basis, basically. All right. One more thing I just want to do, it's kind of a neat problem. I want to find a formula for the dimension of the vector space of skewsymmetric n by n matrices. So if we were going to find a formula for the dimension of a vector space that is n by n and skewsymmetric, it's probably a good idea to first review just what skewsymmetric means. These are the ones where basically these are the ones where like AT equals minus A. So in these problems, like if we take that notation like A sub ij, like an entry in the matrix is going to equal like the negative of A ji, right? Like we flip across the diagonal and negate it, right? So in these matrices, we basically only need to be concerned with the upper triangular part, let's say. So you could take we also have for these matrices that like the diagonal would have to be 0. So if I just let's take like a simple one, like a 2 by 2. Basically, you have to have 0 there, 0 there. And then really, if you put a 1 up there, that could act as a basis for a 2 by 2 one. So in order to get this to actually be a basis for these skew-symmetric matrices, we would want this, though, actually to be like a negative one, right? Because we need across that diagonal to have like this property, right, where there's like a flip of sign. And so that is sort of what the basis would look like for a 2 by 2. And like if I just kind of keep building up, I think you're going to see a pattern here. So for 3 by 3s, 0, 1, 0, oh wait, no, that should be negative 1, 0, 0, 0, 0, 0. Actually, I'm just going to write the other ones down here. So that's what you would get for 3 by 3s. And you can kind of see, right, that there's sort of like a triangle number thing going on, right? The way I kind of think about it is for 2 by 2s, you got like one entry in that top corner that will sort of dictate everything. For the next one, you've got sort of 3, right, entries that will dictate things. And then for 4 by 4, you would have 1, 2, 3, 4, 5, 6 things going on. And you could just keep doing this, but this is like the classic triangle numbers. And hopefully we kind of know that if you add like up to n, you get n times n plus 1 over 2, right? And we did that problem back when we did some induction thing, but that's kind of like a classic result for like the sum of the first n integers, right? But we don't have, like, so for 3 by 3, right, we don't have entries for, like, this is always going to be a 0. We don't need, like, a 1 there, right, because it's skew-symmetric. And so we really want to do not the first n, but we want to do the n minus 1. So 1 plus blah, 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 up to n minus 1. And so what you get is you basically just drop all this by 1 here. So you get n minus 1 times n over 2. And so this is like the amount of basis vectors, and so we can like test it. So we know that we should sort of need like 3 basis vectors for a 3 by 3, right? That's skew-symmetric. So if we plug in 3 for n, right? Just notice, so if n equals 3, I'm just like kind of checking it. You would get 2 times 3 over 2, so that would cancel, and you get 3. So you really do get 3 different, this tells us that we get 3 different basis vectors for that. So in terms of a formula for the n by n skew-symmetric matrices, we could just take the sum of the first n minus 1 integers. That would work. And it's just a byproduct of triangle numbers, which are like super prevalent in a ton of areas of math. So it's kind of neat.